in 1933. And then another paper that came rather later by Kahn and Vulture on the timing mass for the M31 galaxy system. And again, this is a really important and very direct indication that there is dark matter. But it really got very little response. And then I want to contrast this very briefly with the discovery of pulsars and the discovery of dark matter in dwarf spheroidal galaxies, both of which had an immediate impact. And then I'm going to turn to Slipher's work on galaxy redshifts. So first of all, Twicky's discovery of dark matter in coma. He measured the velocity dispersion of galaxies in the coma cluster. He used techniques that are the same as what we use now, Radial theorem, to show that the mass of the coma cluster was much in excess of the likely sum of the masses of the individual galaxies. Similar result came from Sinclair Smith a few years later in the Virgo cluster, and Twicky's velocity dispersion, I should add, and Smith's also are close to present estimates for the cluster. So there's no problem with the data. This profound discovery got little response other than Smith's follow-up study. It took another 35 years for the dark matter saga to take off, and in this case, Twicky in the end did get the credit. Then it took another 20 years to learn that clusters have the universal baryon content, about 16% of their mass, including hot gas, which dominates the baryons, and the rest of the basically cluster is in dark matter, partly in the galaxies and partly in the clusters. I'll just take a moment just to show you some pictures that are probably pretty familiar. This is two examples of clusters which are moving. There's two clusters involved in each case. They're moving in the plane of the screen. They had an encounter, and what you can see in blue is the dark matter, which is associated with the galaxies, and that dark matter is mapped out by weak lensing. And then you can see in red the hot gas, which is seen in X-rays and measured by the Chandra telescope. So you can really see how the dark matter content lies. And this is just really to indicate what sort of followed on from Twicky's work. Why did this profound and apparently straightforward discovery get so little response? Did the community already regard Twicky with suspicion, or did that just come later? Why didn't astronomers follow up in, I think, what would be a pretty obvious thing to do, even at the time, with spectroscopy of groups of galaxies, like the M81 and Leo groups. These are just like smaller clusters, which would in fact be much easier to study than what Twicky achieved in coma. Or was it due to suspicion of results for which there's no existing theoretical framework? I suspect this is a big part of it. It will just come up again several times in the talk. For example, Eddington's quote that it's also a good rule not to put over much confidence in observational results until they're confirmed by theory. This overweening arrogance of theoreticians that we still face. Okay, well, Twicky now does get full credit for its discovery. It's a counterexample to Stiegler's law of eponymity, that no scientific discovery is named after its original discoverer. New big ideas only tend to catch on when the scientific community is ready for them, or an established scientist finds it useful, and I think we've all seen this happening. And particularly, if a statement of an idea comes too early, and a later statement is accepted by the community, it indicates that the community accepts ideas when they fit into their current framework. And this is something we see all the time, that there's no virtue in being ahead of your time. If you make a discovery and it's too early, you're regarded at best as a freak when finally the community catches up with it. At worst, you're completely disregarded. And it's just a fact of life. Yeah. Okay, I don't want to dwell too much on the appropriation of discoveries by others, or the later failure to recognise discoveries like Slipher's. That need not be the same issue as Stiegler's law. But Hubble's name comes up frequently in these discussions. See Michael's talk on Saturday. It's interesting to ask why. I'm aware of at least 4 examples of this kind of thing involving Hubble. Well, there are 2 that we're familiar with at this meeting. One is the lack of recognition of Slipher's redshift achievements until long after the event. His work had impact on the community at the time, but later it didn't get the recognition that it deserved in the context of the expanding universe. And then there's the issue about the Hubble redshift distance law and Lemaitre's contribution, which has been discussed a lot recently. Lemaitre's discovery of the law a few years earlier than Hubble's wasn't recognised properly. The translation of Lemaitre's paper into English omitted, this was a largely theoretical paper with a bit of observational results in it. A translation of Lemaitre's paper into English omitted the observational section which showed that Hubble's law and which showed the Hubble law and Lemaitre's derivation of the Hubble constant. And there's been quite a bit of correspondence in the last couple of years about this and whether it was dirty work afoot. But Mario Livio has argued, and I think fairly convincingly, that this omission was in fact Lemaitre's choice. And this sometimes happens when you get theoreticians who are involved in also some observational work. They see that the theoretical work is much more important than the observational work. And I can easily, having been in a situation like this myself, from days when I was a theoretician, I can easily see how Lemaitre may have thought that his observational contribution really wasn't nearly as significant as the theoretical one and just expunged it from the translation. But anyway, this is something about which there's been quite a bit of work recently. In the book that Owen mentioned that David Block and I wrote a few years ago, we identified two other incidents involving Hubble and the UK astronomer Reynolds. Reynolds was an interesting character. He was a so-called amateur, but in fact he was no more amateur than most of the astronomers in this room. He was a very professional operator. He knew a huge amount of astronomy, had a lot of money. He was an industrialist, and he had a lot of measuring equipment for analysing photographic plates. He built 3 30-inch telescopes, one of which finished up in Australia and was unfortunately destroyed in the fire. But these were fine telescopes. He did a lot of photography, and he got quantitative results out of photography, which is quite a feat in present days. So Reynolds basically invented a thing that's now called the Hubble classification of galaxies. Hubble certainly knew about Reynolds' work, and the two of them corresponded about classification around 1919. The other Hubble law, not the expansion of the universe, but the light distribution in elliptical galaxies, which looks like this. That's a surface brightness distribution, R is a radius, A is a scale. Reynolds discovered this several years before Hubble actually worked on it. It became known as the Hubble distribution, but more recently people have figured out that Reynolds actually did this first, and it's now known as the Hubble-Reynolds law. There's a view that Hubble wasn't generous in acknowledging the contribution of others. Some who I knew who themselves knew Hubble regarded him poorly in this respect. On the other hand, Hubble is not unique in this kind of behaviour. Some of us are careless about picking up ideas and forgetting where they came from. It still happens today. There's a whole bunch of other things that come into it: geography, institutional rivalry, culture. National cultures can also be significant elements in this behaviour. For others, I suspect Slipher is one of them, and certainly Reynolds was another one. Modesty is more important than credit. I won't go on about this any longer. Now, the other example of an important discovery that made almost no impact at the time is the work by Kahn and Bolcher on the motion of M31 relative to the galaxy. M31 is about 750 kiloparsecs from us. It's approaching the Milky Way at 188 kilometres a second. Now, if you adopt the age of the universe, assume a radial orbit, and just simple Keplerian dynamics, it shows immediately that the mass of the system, M31 and the Milky Way, is about 20 times larger than the likely masses of the stars. This was well known at the time. A large, I say here, we assume a radial orbit. A large transverse component of the motion is unlikely, and was recently shown to be small, would anyway make the problem worse rather than better. So Kahn and Bolcher got a total mass for the two galaxies that was greater than 2 by 10 to the 12 solar masses. Recent estimates, very recent estimates, about 3 times 10 to the 12. The distance scale was right, and the stellar masses were roughly right. Their argument is direct and compelling, but in 1959 it made almost no impact. It was brushed off by a couple of unconvincing studies that concluded that extra mass wasn't needed to bind the local group. So here's the picture, just the two galaxies approaching at 180 kilometres a second. Do the Keplerian dynamics, and you finish up with a ratio of dark to stellar mass of around 20. So you know what the stellar masses involved are, and this means you've got a dark halo going up to way past 100 kiloparsecs. So, Kahn and Vulture excluded intergalactic stars, and they argued that the extra required mass was in the form of ionized gas, and the paper went on to explore the effects that this gas might have on the galactic disk. And maybe that was a distraction from the real impact of their paper, that there's a huge amount of unaccounted for matter. Why did the paper have so little impact? Well, their argument is simple and it's correct, and it's survived to the present. They were both very respectable and well-regarded researchers, and if their work had made the impact it deserves, it could have started the dark matter revival in 1959 instead of waiting another decade. My guess is that there was simply no theoretical framework within which to interpret this observation. The weak contrary evidence that I mentioned provided a welcome escape from an uncomfortable situation. Now in the 1970s, this revival that I mentioned here, that started, and it came from 21 centimetre rotation curves of spiral galaxies, and that showed very clearly they had massive and extended dark halos. The argument was really no clearer than Kahn and Vulture's argument, but it did make an impact. And the reason it made an impact was that there was a theoretical framework at that point for discussing dark matter, even though this theoretical framework turns out to be wrong. So this is what I'm talking about, the 21 centimetre rotation curve of a particular spiral has been well studied. This is how the rotation goes with radius. This is what you expect from the stars and the gas together, this one. And you need an extra contribution that looks like this in rotation against radius from a dark halo to give you the rotation curve you observe. And by now hundreds of galaxies have been observed in this way. And it's quite clear that the stars and gas together don't provide enough gravity to explain the rotation. You need the extra gravity of the dark halo. So the Kahn and Vulture story about the galaxy in M31 is dynamically very straightforward. And so is the dynamics of the flat rotation curves. One of these made an impact, and the other one did not. The idea of dark matter from rotation curves started controversially around 1970s. This is a typical, Scott Tremaine has discussed this in terms of paradigm changes. It was a typical sort of paradigm change. It was controversial when it started, but it was based on poor data, but it was taken seriously. So why was it taken seriously? Well, I think the reason is that in the 1970s, the idea of the massive dark halo got unexpected support from theoretical arguments about the need for dark matter to stabilize distance against bar formation. Now, these arguments turned out to be irrelevant because, in fact, most galaxies do have bars. In fact, now we know that dark halos are needed to sustain bars via angular momentum transport. But anyway, there was this theoretical framework in which people could interpret what was going on with this dark matter, so pretty much a dark matter revolution. The controversy ended around 1978 when high quality 21 centimetre curves became available from the Dutch radio telescope. Even though the theory turned out to be irrelevant, people believe observations that fit into a theoretical framework, even if the observations have a sounder basis than the theory, as it was the case here. It allows them to come to grips with startling observations in the way that Eddie mentioned. So here's just to show you what barred spiral is all about, in case you've forgotten. Here's an unbarred spiral, basically a symmetric system. A barred spiral. In the 1970s, barred spirals are thought to be rare. Now we know that in fact they're very common. Most galaxies, including our own galaxy, have a central bar when you look at them in the infrared. And here's just a quick picture of the spiral galaxy M83, first of all in blue light, and then in the K-band in the infrared. In the infrared, the blue stars are not so important, and all this dust absorption becomes transparent. You can see very clearly a bar in this galaxy, which you don't see immediately in the optical picture. Okay, so just very quickly, a couple of unexpected discoveries that had an immediate impact. One was the discovery of pulsars in 1967 by Hewish and Bell. That was followed by a quick stream of papers after a very brief episode that some of you might remember about little green men sending us signals. The focus very quickly moved to the current spinning neutron star explanation. Why did this get such a quick response? Because the basic theoretical framework was already in place from Barber and Zwicky and other theoretical developments. People very quickly made the connection between pulsars and spinning neutron stars. Another example is the discovery of the high fraction of dark matter in dwarf spheroidal galaxies. Now this started in 1983 with two papers and quite different arguments. This was to do with the tidal structure of these galaxies. This one was to do with the velocity dispersion based on 3 stars. In both cases, the arguments were really flimsy, but there was only limited skepticism. Now this dark matter in dwarf spheroidals is still a very active field today. Current estimates of mass to light ratios are over 1,000 for some of the faintest of these dwarf spheroidal galaxies. Why did this discovery get such a quick response? Again, in this case, I think it was because the basic observational infrastructure of dark matter in galaxies was already there, plus the ideas from White and Rees in 1978 about the importance of dark matter in galaxy formation. Okay, so now the Slipher. You've already, even as early as this in the conference, you've heard much of this, so I can go through a lot of this quite quickly. Slipher had expertise in spectroscopy. He wrote a very nice paper on the Lowell spectrograph that was built for planetary spectroscopy to go on the 61 centimetre refractor. Lowell had requested Slipher to get a spectra of these nebulae, but not in the context of extragalactic science, of course. This was a major challenge because of their low surface brightness. Slipher had the expertise, or acquired the expertise, to do this kind of thing. He modified the instrument for nebula spectroscopy, and you probably saw last night the modifications of the spectrograph that he used to do this. This advanced the technology, made it possible to measure nebula redshifts, although, as Laird mentioned in question time earlier, he wasn't really the first person to get into nebula spectroscopy. But for about a decade, Slipher was the only person, almost the only person, measuring velocities of nebulae, although there are mentions of confirmations by Wright, Wolf, and Pease. These people, and Pfaff from Lick, had already acquired nebula spectra, but for various reasons have not measured their radial velocities. So here's the picture you've seen already a few times. Slipher at the spectrograph. Just a few technical things. Nebula exposures were long, 20 to 40 hours. Linear dispersions of this instrument was not particularly low by nebula spectrograph standards. It was 140 tenth meters per millimeter. Now, I never heard of tenth meters until I started preparing this talk. So the tenth meter is an extra in case you're like me and you don't know. This, for people like me who've done nebula spectroscopy in the past, is quite adequate for seeing visually rotation in a spiral galaxy. With the original optics, just for contrast, the dispersion was about 11 angstroms per millimeter, or a resolution of 22,000, which is at the sort of low end of what we would now call high-resolution spectroscopy. So the Slipher papers, again, you've heard much of this, the measurement of M31, and this quote from him that this measuring velocities of nebulae is something worth doing. 1914, he measured the rotation of the Sombrero galaxy. This is a system with a high surface brightness bulge, and that's probably why he was able to do it. Quite high rotational velocity. This would be easily visible just with the naked eye on the photographic spectrum. 1915, he had velocities of 15 spirals. 13 of them were positive up to 1100 kilometers a second. Mean was about 400 kilometers a second. And this is the important point that Slipher very much realized immediately. This is about 25 times higher than the average stellar velocity. By 1917, he did this longer review on the nebulae. How accurate are his velocities? They're actually pretty good. The dispersion against modern values is 112 kilometers a second, which is very close to his own estimate of about 100 kilometers a second. So by 1917, he had 25 galaxies up to 1100 kilometers a second, all positive except for the local group and M81. The mean velocity of the nebulae is now about 30 times the average velocity of the stars. And Slipher really appreciated this very much himself. For a long time, he said, it's been suggested that spiral nebulae are stellar systems seen at great distances. This is the island universe theory, and this theory, it seems to me, gains favour in the present observations. So Slipher was very well aware of the implications and significance of his observations. The velocities are much greater than those of galactic stars. He inferred that the objects lie outside the Milky Way. Hertzsprung had written to him in 1914 to make exactly the same point. And although there are a few, like the Reynolds, who who I've mentioned before, had their doubts about the data. Slipher had a convincing response with confirmation of velocities from others. His work was well known. Why didn't it settle the issue of the island universes? The velocities of stars were known from the work of Boston, Campbell, and Captain, and others to increase with spectral type, as we've heard from Robert, from about 6 kilometres a second at early types up to 27 kilometres a second for the planetary nebulae. And this, I should just add that this effect of why this happens is still today not understood. What the heating process is that drives the dispersion of stars up as they get effectively getting older. They're still left behind. The heating is really not understood here. So the question is, could these galactic objects with their high velocities, 300 or 400 kilometres a second, be just simply further up this evolutionary chain? It seemed unlikely. I think Slipher regarded it as unlikely. Their high velocities indicated that they weren't gravitationally bound to the Milky Way. That's a simple argument which people had the equivalent from what Captain had done to work out the galaxies were just, they were physically, dynamically unbound from the Milky Way. By 1916, there were already some ideas about obscuring material in the Milky Way. It had been long known, back into the 19th century, that the nebulae avoided the galactic plane, which again favoured an interpretation putting them outside the Milky Way at the time. Further observations came from the observations of galactic novae, but the thing that really confused issues was von Maumann's proclamations of nearby galaxies. This, I think, is, I speculate in the end that this is really at the root of why Slipher missed out on some of his credit. So in the 1920s Shapley-Curtis debate, Shapley argued that the nebulae are just nearby clouds and the universe is one big galaxy. Curtis argued that the nebulae are galaxies like our own, far outside the Milky Way. In the end, Hubble's 1923 Cepheid work on M31 settled the question. There's some similarity of this controversy about the island universes and the dark matter controversy that I talked about in the 1970s. There's a similarity in reverse. The dark matter story was supported by erroneous theory, while the island universe was delayed by erroneous observations. And I think the point we learned from this is that the progress is not always linear. I conclude that Slipher's situation is not at all comparable with Swicky's. Slipher's work made an impact at the time, but his problem with recognition came later, because of course Swicky's was exactly the opposite way around. I'd speculate that without von Maumann's confusion, this issue would have been more clearly defined. Maybe the debate would not have happened, and Slipher would have got the credit for identifying the nebulae as extragalactic, which I think he deserves. So, my last slide, in conclusion, I still find it hard, after reading more about this, I still find it hard to believe that the high velocities of the nebulae were not regarded as conclusive evidence for their extragalactic nature. Slipher had shown convincingly that the wavelength shifts in the spectra of the nebulae were consistent with the Doppler shift, and others had reproduced these velocities. Captain had already made a fairly accurate estimate of the mass of the Milky Way and seemed clear, even at this time, that the nebulae could not be bound to the Milky Way. So I think Slipher is very unfortunately missing out on this. Thank you.
Okay, you stay here. Answer some questions. That quotation from Eddington, Cecilia Payne-Krapashkin said how startled she was when Eddington said he wouldn't believe an observation unless it had a good theory behind it. And she asked him why in the world he had said something like that. And he said, oh, I just wanted to shake up Rutherford a bit. She has some questions in the back.
Could you say a little more about what von Maumann's erroneous observations were?
Yeah, sure. Von Maumann had used photographic observations separated by some length of time to look for the transverse motion of objects in M101 and I think also in M31. And he has found an effect. Now it's a very subtle, measuring proper motions even for stars is quite a subtle thing. A lot of things can go wrong, and a lot of things did go wrong. And by 1925, I think his work was discredited. I can't really go into the technicalities of this. I'm not sure exactly what went wrong. I suspect I know, because just of the way that he made the comparison of where stars were in one epoch and where they were in another epoch. But anyway, he had some respectability, and he was taken very seriously. But then in the end, a few years later, his work turned out to be wrong. It came at just the wrong time for the debate, the Curtis-Shapley debate, and certainly for Slipher. I think if this Freeman thing hadn't happened, the evolution of this whole thing may well have been different. Hale may not have even wanted to stage this debate at the Academy, and I think history could have been quite different.
I thought I'd also read that when Hubble made his discovery of the Cepheid and Andromeda, that he was at the same institute as Van Manen, and Van Manen had these crazy plates, and it drove him crazy that this guy was saying that what he had discovered wasn't possible because of this exact problem. So are you sure it was 1925 he was already discredited? Because Hubble was quite concerned about it in what I've read.
I mean, that 1925 may have been a bit generous. I mean, really, by the time Hubble had done his thing in 1923, the story was over. But I think there must have still been some worry. Robert may be able to say more on this, but it was still. I mean, my sense of it is by 1925, Freeman was really out of it.
You're next.
Thank you, Ken. Surely part of it, though, is again, it's a reluctance to accept that these are Doppler shifts and they are representing radial velocities. I think that there's a reluctance there, and I can understand it. You gave the answer yourself. It's because there's no explanation for that. Why would they be rushing away? In a Newtonian universe, which it is at this stage for most people, there's no underlying explanation, and so I think it's perfectly normal for a lot of people to assume that maybe these aren't what they look like. Maybe it's some other effect, peculiar motions or whatever else that's possibly to say.
Yes.
What age of the universe did Kahn and Walter use?
It was a bit longer than the present. I think
17 billion years?
My recollection is 18, but it doesn't make a hell of a lot of difference.
Joe?
Could you say when Kapteyn estimated the mass of the system of stars and how well accepted that estimate was?
It must have been just somewhere. It was around the time that Kapteyn was making his great model. So I think I may be wrong, but I think that was around 1905. But somebody could certainly correct me on this. I think it was pretty well accepted, because I've never heard of anyone quibbling with it. And it's a very reasonable Newtonian estimate, just basically based on the motions of the stars at the time. So.
Oh, okay.
Kapteyn never accepted the existence of interstellar absorption when he made some of those calculations. And of course, after Shapley's galaxy turned out to be so much larger, you have to factor that in to your third conclusion. That certainly was a game changer.
Yes. Okay, one last question.
Well, from the sublime to the ridiculous, fill me in on the little green men.
I was around Cambridge at the time when this was all breaking, and they thought just for a moment that these were signals from extraterrestrial civilization. But I don't know if this was ever taken seriously. I recall seeing this in press, but I couldn't find it when I was looking. But I remember the buzz going around Cambridge that this was the hot thing. But it really only lasted weeks.
Led to the timing of the Great Debate clearly wasn't a watershed in observation. That's the full picture.
Well, the timing of the Great Debate was that relativity was such a big issue at that time, and the Academy was much too conservative to hear anything of that. So they figured they could have a nice debate between Mount Wilson and Lick Observatory, and that came about in 1920 as sort of an after-dinner conversazione at the Academy. All right, thank you.